It is a pleasure to introduce Paul Horja from the University of Miami, and he will be speaking of a categorical description of discriminants. Paul, thank you very much.
Thank you, Lupercio. So, the title of my talk contains the word categorical. So because of that, what I will try to do is start with something which kind of is very elementary and classical, and then sort of move towards the categorical story later. Okay, so that's kind of the general idea. I'll start with some classical things, some combinatorics, and then, as I said, push the categorical statements towards the end. So this classical notion of discriminant, so you start with a polynomial of degree n, and the discriminant be classically defined. I think the name goes back to Sylvester, I believe. I looked it up 2 days ago. Is a polynomial in the coefficients such that the polynomial is 0 if f has a double root. So, so these are the ones that you sort of compute in elementary school, maybe a little later in high school. And here is one that I'm not sure that you ever compute by hand, but it's out there. In fact, there is a website where you can enter a polynomial and it computes for you the discriminant. So, so despite of being, as I said, a very classical problem, the amazing thing about this story is that there still are many questions about singularities of discriminants that are not answered. And in about late 80s, early 90s, Gelfand, Kapranov-Zelevinsky came up with a new approach to discriminants. And they wrote a book, this remarkable book, the Green Book, in which what they do, they take a new point of view on the theory of discriminants, of this classical theory of the discriminants. In fact, the book has an appendix, I believe, where they even analyze one of these old papers, maybe Cayley, I believe, something like that. So they really do look at history and come up with some amazing new machinery. The work itself, it actually looks like it's been inspired by some work they've been doing in regards to the so-called Gelfand-Kapranov-Zelevinsky system of linear partial differential equations, which is also relevant for this talk, but I will not touch directly in this talk. So it will be kind of in the background. So what's their notion of discriminant? So you start with a what I call at least a set. I think that's the terminology that people use. I'm not sure that Gelfand-Kapranov-Zelevinsky do that, but basically it's a finite set of vectors in a lattice such that sits in a hyperplane at distance 1 from the origin. So for technical reasons, this condition is important for their approach. Of course, we can start with any set and then either raise the dimension or move it into a hyperplane or something like that. So that is something that people do in the field. So in terms of notation, I will use Q, which is a little unusual. Usually people call this delta for the convex hull of this set. K is the cone over the vectors. over the convex hull if you want. And then in this context, we can talk about exactly about the classical discriminant. So you write the polynomial, in this case, it's going to be the Laurent polynomial, and you're asking the question, when is this Laurent polynomial going to be singular in the open torus? And this is exactly that. That's not necessarily. I mean, it's not definitely a GKZ story. You can write the classical discriminant. We're going to call it delta A. Is that irreducible polynomial whose zero set is given by the union of all the irreducible codimension 1 components of this Zariski closure. So one important observation: the components may be wild here. So we already have a very complex problem where the codimension of this nabla A is greater than 1. The convention is that you set the, I think that should have been delta here. You set delta to 1. So what happened a bit before the Gelfand-Kaprano-Zelevinsky story, in fact, in the work of Danilov and Kovansky, this was certainly before that, and then Batrev used this in his paper on mixed Hart structures on toric varieties, is that it looks like a very useful notion, very useful idea to consider a more general notion of regularity. So namely, instead of just looking at the Laurent polynomial defined by all the lattice points in the polytope, we can also look at the Laurent polynomial defined by the restriction of the two non-empty faces. So, you can, for each of those, you can define one of these classical discriminants, delta, and then the magic gadget, if you ask me at least, of this theory of discriminants is this notion of what they call a principal A determinant. There's good reasons why they use the terminology, is the following polynomial. So they call it EA, and it's a product. So there, it's over all these discriminants corresponding to all the non-empty faces with some multiplicities. So everything here is crucial for this definition. Again, the idea of considering regularity, considering these versions of the discriminant for all the restrictions to the faces goes back to Danilov and Kovansky. Now, these multiplicities, and for us, these are crucial. That's certainly something that is very important in the theory developed by Gelfand-Kaprano-Zelevinsky. So you're taking all the faces, as I said, all the non-empty faces. One observation here, as it turns out, in fact, the only interesting factors in this, well, interesting in the sense that the other ones are 1, are those when this A intersected gamma is doesn't generate a basis of the lattice, of the restriction of the lattice to the face. So you sort of take for each face, you restrict the underlying lattice, and then if A intersected gamma gives you a base of that, then this is going to be 1. So in a way, we're really capturing here the combinatorics, as I said, of the faces, which are not only they're not simplicial, but they're not even unimodular. So simplicial, anything which is, when in the case then A intersected gamma is a unimodular basis, you get 1. So those don't count sort of in this sum. Okay, so let me say a few words. I'm not going to be able to, this is a little technical, but as I said, it's crucial for us. So I will not say much about, I don't want to go into all the details about defining these multiplicities, but that's an important aspect. So first of all, what's up with the I of gamma? Is exactly sort of what you'd expect that, as I said, that comes up in this story, in fact, is the index of the lattice generated by A, if you want, inside the underlying lattice N when you restrict to this base gamma. So it's going to be, basically the index of a finite group, and that's what I is. Now, U is a little tricky. So what you do basically is the following. Again, think about the polytope, or you can think of either the polytope in a hyperplane, or you can think about the cone over this polytope, and you take one face of this cone, and you do a you take basically you quotient out by this face, and so the red thing here is supposed to represent what the sort of these points are the points that you get inside this quotient, and they come out of the set A. So even though A might be satisfies this hyperplane condition, when you project onto one of these subspaces, that's what this picture is supposed to represent. What you get here is there are some points which do not live in a hyperplane anymore. So the definition of this U corresponding to a face is basically if you want the volume of this what's pictured here in yellow. So basically, you take the cone over the red and you remove the part generated by the red boundary without the vertex, and what you get here is a finite number, the volume, or if you want the number of, in some sense, this is kind of equivalent to counting lattice points. That's important in this story, and that's kind of the U. So, and it's sort of not easy to understand the connection with geometry, but as a sort of preview of what follows, think about the following: that for those that are familiar with, for example, with computations of Grothendieck groups for toric varieties, it's known that those are the rank is given by the volume of the polytope. So this is kind of the analog of this, and it turns out that this analogy is actually pretty direct. So now to any such set, going to geometry, we can associate two toric varieties. In fact, they're really the two sides of mirror symmetry. So one of them is, and this is kind of, again, for those familiar with toric geometry, this is kind of a classical notion. What you do, you take the dual, you take the cone K. Remember, the cone is the cone over our set. You take the dual of this cone, the lattice points inside this dual cone, and that way you obtain a spec of this ring, or is going to be a toric affine variety with Gorenstein singularities. So in a way, from the point of toric geometry, this what we're doing here, where in fact one way to say to present the discussion is we're trying to understand the geometry of the resolutions of this Gorenstein singularity. So in fact, in that sense, that's not that far from the previous talk. And that's one side. The other side is now, so this, as you see, I moved here to the dual side. If I stay on the side of the lattice n, and this is again some known story in toric geometry. This would be kind of the fan side. So now, if I take a simplicial fan supported on such that its rays are the elements of the set A, and you think about this as the fan of a toric Deligne-Mumford stack, what you get here is the Deligne-Mumford stack, which it turns out to be also Calabi-Yau. In other words, the canonical sheaf is trivial, and which comes with a natural Kreppen birational morphism into of the singularity, the Gorenstein singularity Y. So, as I said, in some sense, the idea here is that different triangulations or different stacky fans supported on this cone are going to give us different toric birational equivalent models, which are all birationally equivalent. They're Kreppen resolutions of the same singularity. So, in a way, from the geometric point of view, what we're trying to understand is how, this toric birational geometry picture, which has been, discussed for a long time with various techniques. So the other, besides EA, but related to EA, the other amazing construction of Gelfand, Caprano, Zelebinsky is this the secondary polytope. So basically, they gave a combinatorial formula about how to construct a secondary polytope. So it's generated by these characteristic functions. So for all simplicial fans, if you give me a simplicial fan, I'll tell you what the function is defined at a certain vertex. So for each vertex I take the volumes of all the simplices that contain the vector v, which is a little weird, and I wouldn't do justice if I even doing an example here. I'm not sure it would be very illuminating, but without going to the details why this works, I'll say, at least for those of you who are not familiar with the notion itself, I'll talk about its relevance. So the theorem, the remarkable theorem they prove, is that the Newton polytope of the principal A determinant coincides with the secondary polytope. So you see, this is going back a bit here. So this principal A determinant is this classical notion, roughly speaking, of the discriminant, right? So somehow, which in general, if you look at this literature in the 70s and even later, even today, even nowadays, people try to understand the singularities of discriminants. So that's a very difficult problem, understanding how it looks. And so what Kapranov, Gelfand, and Zelebinsky are doing, they're saying, look, if you, on one hand, if you don't restrict your attention just to the set A, but also to its restrictions to the faces, and then you add this multiplicity, then I have a fantastic recipe for telling you what the Newton polytope of this polynomial is, or Goron polynomial. Sorry, yeah, it's a polynomial. And the magic of it, as far as mirror symmetry is concerned, is that this secondary polytope, or its dual secondary fan, provides a toric compactification of the modular stack of complex structures. I phrase it this way. Symplectic geometers phrase it different ways. It's also connected to the moduli space of Landau-Ginzburg models that Ludmil and collaborators studied in various other context. So, okay, so this is the famous cover of their book, and what this picture is so basically there is a set. The set that they're considering, A, is this. Actually, I shouldn't draw the this is the set A. And and that's the triangle is going to be the secondary polytope. So the way you should think about it, as I said, is kind of a parametrization of various ways of subdividing this into polytopal subdivision. So at the vertices, the vertices correspond to triangulations. So you see, this is a triangulation, this is a triangulation, this is a triangulation. You may say, hey, this is a triangulation and it corresponds to an edge of the secondary poly. It turns out it's not, because in this story, the part that I'm kind of suppressing here is that these are marked subdivisions. So the presence of this point there makes that non-triangulation. I don't know how you call it. So the same story here, and obviously, and in the middle we have that. So this is kind of a closed set, and that's the general story. So the secondary polytope will always have this property that at the vertices you get these triangulations, which give you toric dilemma for stacks, which we can view as any of them is a perfectly fine Krepan resolution of a toric singularity, including in this example. So if you want to understand these, in a way, kind of clever way, the toric variety is associated to some of these, life is a little tougher. You would have to go into the world of Artin stacks, and some people have tried it. I tried it. It's not easy, but somehow the point of this talk is that sometimes we can overcome this issue. So now, what the analysis is that, yes, as I said, the vertices, we have a very good description for the edges, actually, also done in this book. So the edges correspond with what's called the circuit. So a circuit, if you have a bunch of vectors in this set A, and which are not linearly independent, but they're minimally linearly dependent. So there is one unique relationship, and this is this star subdivision, or modification of a triangulation. So this is kind of also a well-known story. And what in this picture, this is what's going on. If you think about this is what's going on along the edges. There is no good description for the general faces, although it's understood that they do correspond to polytopal subdivision, exactly as this picture suggests. So, so the intuitive picture that I always keep in mind, sometimes better to start with this one, I didn't do it today, is the following, that, as I said, we have a moduli space, which in mirror symmetry, since this is mirror symmetry, could be the complex moduli space on one side, or what's called the Kähler moduli space, which hopefully can be we described using this machinery that Ernesto was telling us about, because I tried to get out of him. And so there is this moduli space. At various points in this moduli space, if we look at on this coherent sheaf side, so what's called B side usually by physicists, we have various birational models. So for example, x and x prime are birationally equivalent. So there is an equivalence of categories. This goes back to Bondal-Orlov, Kawamata, and many other people. And this is going to be given by a Fourier multifunctor. Now, the interesting part, so what's interesting about this story, that what bothered me for a long time, is that this question about what's going on along the discriminant lobes. And if you think about singularity theory and discriminants, there is some kind of method for dealing with this, and that's what this conjecture of Aspinall, Plesser, Wang in 2016 is a proposal for this categorical story of discriminants, and it kind of fits well with this five-psi story about vanishing nearby cycles that exists in singularity theory, and it also bodes well nowadays with the story introduced by Kapranov and Shechtman about Schober's. So in a way, what we're trying to build here is a Schober on this moduli space that captures the toric birational geometry of this. Okay, so I need to say, so as I said, that these equivalences are Fourier-Mukai functors according to this, as I said, the story by Bondal-Orlov and Kawamata, and as I said, many other people here. Sorry for it. So the question is, what's going on along the discriminant loci? So what Aspinall, Plesser, and Wang did, they proposed a category, combinatorially, what the categories that should be attached to each component. So each component here is combinatorially defined, and they really have a recipe for that. But before I do that, I have to say something about the wall monodromy spherical functor. So basically, one could prove a theorem, and this wall monodromy is a little bit of misleading term. It is a true monodromy if you think about the mirror side, but here we're talking about bounded derived categories of coherent sheaves. So the theorem says that for any edge of the secondary polytope, there exists a toric stack and an associated spherical functor, where X is the ambient toric stack, and ZF is category defined by the combinatoric. So if we go back to this picture, so you see an edge of the secondary polytope in the moduli space will determine a curve in the moduli space. So what this functor corresponds to is sort of the action of this loop at the categorical level. So I'll say a bit more about this, and then what I promised and what is in this proposal of Aspinall, Plesser, and Wang is this construction of, as I said, of a category corresponding to each component here. And the construction goes like this. So you take a non-empty face, as I said, and you define a stacky fan basically by doing something that I already mentioned when I talked about indices. You sort of take the lattice and the sublattice generated by the intersection of the set A with your face, and you project this the lattice N. And it's a natural way to describe a stacky fan living in that in this finitely generated abelian group. So the complication here is that this space is not a lattice anymore. So that has to do with this story about torsion, which it plays a crucial role here. So this is really, the whole story is based on understanding this for toric stacks, studied by Borisov, Chen, and Smith some time ago. So without that, and there is a further ambiguity in the sense that here that when you project, when you do this projections, you may get various, you make the vectors in A that project into this sublattice are well defined, although the stacky structure, the way you divide them into stacky fans is not. And it turns out they actually give rise to equivalent bounded derived categories for coherent sheaves. And more remarkably, this is crucial for this story, is that the rank of the Grothendieck group associated to this stack is exactly U of gamma times I of gamma, which is sorry for going like I know how else to do it, is the index that shows up here. So that's a hint, as I said, that basically what we're trying to do is, in a way, write down a categorification of this principle, A determinant. So let's call this dB of Z gamma, because Z is in this EZ story, the variety that sits on one hand, on one side of the definition is called Z. And then the conjecture then made, as I already kind of mentioned, is that for each phase gamma, there exists spherical functors of this form, dBz gamma to dBx, determined by a triangulation where x is one of the versions of the birational model for the underlying stack. So going back again to this picture, what the claim is that there is along each discriminant locus, there is a category, and then there is also associated to it, there is a spherical functor from the category on the component to the ambient category. And now with this construction, we really do have a very specific proposed combinatorial construction for this Z gamma. And then with Ludmil, we're conjecturing a bit more than this. So namely that for each edge, the category which showed up in the wall monodromy story can be written as a semi-orthogonal decomposition with a certain number of components of the form dB of Z gamma. Which in particular, if this is true, then part one is true too. So both 2 and 1 are true in examples, of course, so if that's our intuition is based, and there are some kind of serious reasons why you think that's true, but of course it's a conjecture, and we really don't know how to go about proving this in general. But we have some evidence of the result. Our result is some evidence about this conjecture being true. And this kind of, the fact that 2 implies 1 is a consequence of, as I said, of this work by Kuznetsov and Alcorn-Leister-Shipman, which kind of show that if you have a semi-orthogonal decomposition of one of the categories involved in the definition of the spherical functor, then you get a bunch of spherical functors for each of those components. Okay, so our theorem, basically, if we have such a semi-orthogonal decomposition, certainly would be the case that we have a relationship in the ranks of the Grothendieck groups, and we prove this. So we prove that indeed exactly what we expect, that the rank of the Grothendieck group of the base category used for the wall monodromy is a sum with some coefficients of the ranks of the corresponding categories to the components of the discriminant locus. So the important aspect of this story, of course, is how do you define these multiplicities? And this is a little complicated, and for people who have thought about discriminants, they may know this multiplicity story in the world of discriminants is a very subtle problem. In other words, if you have components intersecting in certain ways, it's hard to define the true multiplicity. This definition, though, our definition is purely algebraic and combinatorial. So we can really write it down with a computer code. The computations may get hard, but a computer can do it. And in the good cases, it really coincides with what you expect geometrically. So basically, the proof of this, I'm not going to go. It's a little technical, but not very technical. It's in a way what we're doing. We're analyzing the asymptotic properties of this A determinant. So it's in spirit is a proof, kind of in the spirit of toric geometry, and so you kind of look at the asymptotics of this A determinant, and then when you compare the asymptotics, basically the crucial object here is this discriminant associated to a circuit. So I'll remind you, a circuit is this minimal set of vectors which are linearly dependent but not linearly independent. And you compare in two ways this expansion, and then we compare the multiplicities, and really those boil down to be exactly these ranks of K theory. So that's kind of based on, as I said, on analysis of this asymptotics. So okay, so let me do some examples. So let me go now to the first example. So you see, this is kind of the first example. Why? Because if you think about what that set is so you have 0, 1, 2, 3, 4. So if you write down the Laurent polynomials associated with this picture, you're really going to get such that this is the Newton polytope, if you want, or the cone. You're really going to get exactly the polynomial degree 4 that was discussed in the beginning. And it turns out this is kind of a story that is known, that the secondary polytope is combinatorially equivalent to a cube in R3. Not obvious, but basically you want to understand how many ways you can triangulate, and what are what's the meaning of the faces of the cube. That can be done very precisely. And I'll remind you, I already wrote this, that this delta Q is exactly the formula that was presented in the beginning. There is some addition here, A0, A4. I'm not going to go over that. Why is that relevant? But it is relevant in the story. Basically, it has to do with the fact that when you write down EA, you always have to look at boundary faces. In this case, these are their 2 points, or the boundaries of the cone. So that corresponds to this A0, A4. Yeah, so I should have said here, sorry for going back. So this proof is in the spirit of actually a tropical geometry. So that's another connection kind of with what Ernesto was saying. So this is really this looking at the asymptotics of this A determinants is really an idea that it's used a lot in when you do tropical geometry, and that's kind of what we're doing there too. So now, okay, so there is not much to say in terms of basis of the polytope. So our polytope here is this really is just a segment. So this is the Q. So there are two boundary points. Well, that they play a role, and I won't go over the role of that. But the point is this base category corresponding to the idea is that we'll have this very complicated component corresponding to Q, and along this component, the category in this case is just dB of a point. So this dB of the point, sort of, intuitively you think about it, as I said, sliding along this discriminant, and what happens is that you get these spherical functors into the ambient dB of x, where dB of x, where x is one of the stacky resolutions obtained by considering one of the possible triangulations. So for example, the easiest one to think about is this one. So 0 and 4. So you ignore all the points here, and that is going to be from the point of view of stack the limit for stacks. This is going to be C2 over Z4. And for example, if we try to connect this to so this is going to be to this triangulation or this stacky structure, there is an edge. We know this. There is an edge in the secondary polytope capturing that picture. There is a circuit relation, something like 3V0 minus 4V1 plus V4 equals 0. As I said, to each circuit, you can associate this gadget, the discriminant, if you want, the local discriminant associated with the circuit. That's kind of familiar from cubic. Well, I guess it's not quite it, but it looks like familiar with the cubic story. And you see, in fact, yeah. So this, as I said, plays a crucial role here. Why? Because I'll take it back. This should not be cubic. Actually, it has to do with a degree 4 polynomial of a certain shape. But the main point, and that's kind of a remarkable thing, is that if you go back here, you can actually identify, so I should have done this beforehand, kind of collect those terms show up inside this, there are two of those terms. As I said, 256, if you don't believe me, you can look at the slides later. But it's going to be something like this, A4 squared times delta I. And then, so that the fact that here there is multiplicity, this delta I shows with multiplicity 1, tells us that the spherical functor is of the form dB spec of C with values in this dB of the ambient stack. Now, if we do another one, so now if you, instead of looking at something like this, if we look at 0, 2, 4, of this subdivision. This is also going to give a toric stack, which is a little different than the previous one. The circuit, there is, again, another circuit relation associated to this. Again, as I said, to this circuit relation, I have another delta I, A0, A4, minus 4. So then the leading term here with respect to this asymptotic expansion is going to be, so what we do, we look at that humongous formula that I didn't know how to have it so that we can have it on the same time, but these are really three terms collected from that formula, and it turns out that this is 16A0A4, this discriminant to the power to the second power. So what that tells us is that the spherical functor now, that multiplicity is 2, and that is basically the rank of K0 of this toric stack. So I have another example. So as you can tell, the example actually doing this and trying to verify the conjecture with discriminant, it gets really hairy very quickly. So that's why, in a way, this is a baby example. So this, I have another baby example. I mentioned this, I think, also in when I gave this version of the stuff in Bulgaria. So with the classical baby example, this goes back to the string theory papers in the 90s. So you start with weighted projective space with weight 1, 1, 2 as a Z2 singularity. You blow that up, so you kind of do the usual projection of P1 by removing the bad locus, and you blow that up, and what you get is actually Hirzebruch F2. So that's one way to get the Hirzebruch F2. I'll describe the combinatorial picture on the next slide. So what we have here now, since we're talking about, you see our Calabi-Yaos are toric, so that means we're talking about quasi-projective Calabi-Yau. So we have to lift the dimensions. So of course F2 is not Calabi-Yau, but its canonical, this total space of the canonical bundle is going to be. So the question is, the diagram is of the following sort. You have the total space of the canonical bundle, the stacky total space of the canonical bundle of the weighted projective space. Here, there is something weird, but it's a vibration over the total vibration over P1. This is kind of something called the hybrid phase. And then finally here, there is the stack of C3 over Z4. So basically, so let me go to this. Yeah, so the vector configuration describing F2 is this one, probably familiar to people who do toric geometry. So you see, we have various, this is one possible triangulation, this is another one, this is another one, this is another one. So here, this is the one corresponding to the weighted projective space. Here we remove the central point, and here we remove both that and that, and what we get is this stack. And that's the combinatorial picture captured by the secondary fan. I also drew exactly the analog of the picture from the cover of the Gelfand Kapranov Zelevinsky book. Well, it doesn't look like I've drawn all of them somehow. I've drawn, oh, I see, because I think I'm only concerned with these two sides of the picture. So you see, these are the polytopic subdivisions. They may look like a triangulation, but they're not, because there is a mark point here. In this case, there is a mark point there. So from the point of view of, from our point of view, these are not triangulations of the initial set, which had 1, 2, 3, 4, 5 points. And so kind of the way we think about this, I wrote here the explicit form of the vectors. There, you always, the relevant relations between them. That's how you compute, in this case, the Picard group. So this, the picture here upstairs, the birational picture, the geometric pictures, is completely captured by this combinatorial picture. And I put this here for people familiar with the secondary fan story that also got mentioned, I think, by Ernesto. And this is kind of the secondary fan picture of this. So again, I copied it here. And then now the moduli space picture that one can write down is something like this. So you see, first of all, going back to this configuration, actually it is here too, our vector configuration has, what are the interesting faces, so to speak. So there is the big one. Certainly that's not unimodular, actually. It is simplicial, but there are these interior points. And there is another interesting face, 1, 3, which has 2 inside the edge. So when you write down the principal A determinant, there'll be 2 factors. One coming out of the big face, so to speak, and one coming out of this edge 1, 3. And on this picture, this is going to be what I call here D delta. That's a component corresponding to the big face. And then the component corresponding to the edge, I call this D gamma. And there is some, geometry involved in this. So this is another way to picture it. And so what are the, so you see now, what are the wall monodromies? The wall monodromies correspond to sort of staying here, corresponding to this component y equals 1 over 4. So there you can go around this component this way, or you can go around this component this way. And it turns out that geometrically they're very different operations. So if x is constant, and if it infinitesimally close to sorry, I meant here x equals 0, not y equals 0. So you should think about a kind of a loop going along this way. So again, imagine this is a picture really representing which naturally lives in C2. So, and we use the projection using, say, the moment map to get this picture, R2 picture. And this should have been x equals 0. So, so in other words, this loop is going to be the spherical functor where z is actually a1. And if we do that here, we're going to get a different z. We're going to get the stacky version of this. Of course, the point here is that of our conjecture with Ludmil is that the z has a semi-orthogonal decomposition where I have here z1, sorry, I have this Z as one of the components of the semi-orthogonal decomposition of A1 stack quotient stack by Z2. So, so sort of the geometric picture here captures, as I said, the combinatorics of these intersections, and there is some essential tool, as I said, are these computations of the multiplicities. So, okay, so questions and remarks. So the main question for me, at least, in this story is there an analogous story for higher dimensional faces of the secondary polytope? So, so what do I mean by this? You see, in general, let's go to, so even here, so this polytope, the secondary polytope defines, as I said, some kind of projectivization of the moduli space. Depending what you want to do, could be complex structures, as I said, could be even Landau-Ginzburg models. So all we're doing here, in a way, is going along the edges of this polytope. And this is, as I said, something that has been done by many people, including Ludmil in previous work. So it's still the question, what's going on with the toric strata inside this moduli space, which are higher dimension, not just these curves. And well, I have a proposal. I didn't write it because I'm afraid to put it in writing. But the part that is not clear, though, is this part about the semi-orthogonal decomposition. So that certainly is not going to be the same story, but I think it will be interesting if we can work it out. And so if someone is interested, can ask me. Okay, so the conjectural semi-orthogonal decomposition, it looks like, when you write the semi-orthogonal decompositions, it's a little misleading in its in how simple it looks. In fact, the maps that determine this semi-orthogonal decomposition, besides the fact that you have some vanishing of columns or something like that, are a part of this definition. And it turns out that in this case, the structure of those semi-orthogonal decomposition has to do with some braid monodromies in moduli spaces of this type. And there's something that I guess Nina and Anatoly actually spoke here about it. So so that's kind of an old story starting with Zariski. So this is certainly a different point of view. I've done some work with Aspinall and Karp along these lines. Again, doing it by hand sounds very complicated, but certainly it looks like this is pointing to some braid monodromy categorification story. So, okay, so now the other interesting, at least as far as I'm concerned, phenomenon going on is what's going on inside a discriminant locus. So moving inside the discriminant locus, if you remember, there is some category that the derived category is not changing, but its core, the T structure, is changing. So that there is some complicated wall crossing phenomena, and it sounds like this should be some correspondence of the some kind of Riemann-Hilbert correspondence. Well, as I already mentioned, this smells like we should be able to capture all this complicated structure by just writing a definition of a Schober. This is hard to do in this case, and I think various people have done, including Kapranov and Bondal and maybe Schechtman and I think Donovan. There are bits and pieces of this. The advantage of this toric case is that you have this combinatorial structure that should allow you maybe to define such a Schober. there is also some older work of Bressler and Lunds, which also is in the spirit of this construction. So I looked a bit of that. That's something interesting. Okay, and then finally, I already mentioned, is there a Landau-Ginzburg version of this? And I think there is. I don't know how interesting it will be, but because it's going to be very similar to this, but certainly that should be analyzed. And finally, there is a relationship kind of underlying all this to the Bridgeland stability conditions. So this moduli space of Kähler structures that showed up at this, even at this conference, and as I said, in Ernesto's talk, is in a way some kind of version of this Bridgeland's space of stability condition. Maybe I should put here geometric Bridgeland stability conditions. So Ludmil has thought about this, but there are some, I think, some written papers of his about this theory of limiting stability conditions. So what happens is that when you approach one of these discriminant loci, from the point of view of the stability conditions, what you're doing is really defining a limiting stability condition. So collapsing in a certain very interesting way the stability condition on the generic category. How this is done is not understood in general, but I think, again, it looks like this construction, just the fact that in this story case we have this combinatorial tools may help shed some light on this story too. So I think so. That's it. Thank you very much.
Thank you very much for a very interesting talk. Questions, anyone?
I have a question about this conjecture, the discriminant conjecture. So in singularities, there is this very important class of singularities related to the units approach of resolution of singularities. These are the singularities where the discriminant also is homomorphous. Okay. Is the conjecture verified in this?
No, it's not, but that's the first case, because you see when, so all the complications indeed start from, so when you have a normal crossing divisor, the fundamental group is a billion.
Yes.
So life is good.
Yeah.
And then indeed, I haven't thought it specifically, but I think in this case certainly it can be said much more than in the general case. So probably analyzing this even should be really possible to analyze this. I mentioned this work I've done with Aspinwall and Karp. This is really order 2. I mean, it's order n, but it doesn't matter. Even in order 2, so then the story gets a little, you have a knot and a torus knot, 2, 3 torus knots, so it's much more complicated. Even this is much more complicated. So this one, yeah, I agree, but we haven't done it, but yeah. Good point.
And the multiplicities that appear in this relation that you put in Katsarkov, are they some sort of Hilbert-Simon multiplicities? Or do you know what they're? What's the algebraic description?
I mean, the way we do it is really, I mean, here, the algebraic, when they, like in the case like this, if the tangency of order 2 is order 2.
So it's some sort of intersection.
Yeah, so here would be order 1, for example. Yeah. The issue is that, of course, these discriminants, sometimes they're like stuff like this, and I can't compute it by hand, but if you work with the discriminant. On the other hand, combinatorially, as I said, there is some, there is a recipe. Plug it into a computer, and it can give you a number, 77 or something. Where it comes from, I don't know, but it gives you a number, kind of. But so that's, so I thought trying to generalize this looks pretty hopeless exactly for this reason, in fact, that in general, even if you have another something going this way, or who knows what tangents, then it's very hard to compute, as I said, with classical tools. But here with this, you write down as I said, a bunch of monomials, and you analyze as I said, asymptotically, and you see the power there, and that's it.
Any other questions? Well, let's thank the speaker again. And we will be back with Alberto Berhovsky at 2 p.m.